Well, boom, just like that, we're back in the Algebra 2 jungle as we focus on statistics, and we're going to spend the second day on this title of sampling variability within the sample proportion. And again, variability measures the spread of our data, and we use the standard deviation to measure that variability and just to see how much variation there is from one sample to the next. And we're going to get a chance to really re-emphasize a lot of the big concepts we saw yesterday, and hopefully we'll continue to build our confidence in those concepts. And today's focus is going to be on flipping a coin and using that 50-50 percentage that we expect from flipping a coin to answer some other questions and how likely some other proportions might actually be as we consider whether they're possible or not. So the number one thing we want to re-emphasize from yesterday is this concept that we're going to talk about in purple right here. And we're saying as the sample size increases, it gets bigger and bigger. So we go from flipping the coin 10 times, and all of a sudden we flip it 50 times, and all of a sudden we flip it 200 times. The sampling variability in the sample proportions decreases. In other words, our data becomes more consistent and our mean should get closer and closer to 50% with regards to the coin. Or in other words, the standard deviation, which is another word for variability, of that sampling distribution of the sample proportions also decreases. Okay? So let's test that theory and apply it to this problem right here. And what they're saying is below there are three different dot plots of the proportion of red chips in a container. So imagine a container, you can't see into it, and let's say there's maybe 200 chips total, just roughly. And we're not sure how many of those 200 are actually red chips or not. So we did one simulation where we pulled out 20 red chips and repeated it several times. Another simulation where our sample size was 60 and we repeated it a number of times. And then yet a third one where we pulled out 120, recorded each chip, put it back in, shook them, pulled out another, just like we did with the beans yesterday. And using the mean, the standard deviation, and the distribution of the dot plot itself, determine which is which. So basically we're saying one of these dot plots corresponds to 20 simulations, one of them corresponds to 60, and one of them corresponds to 120, and it's our job to use the clues that are given to figure out which one's which. Now go back to that first statement we just wrote in our notebook. As the sample size increases, okay, and it goes from 20 to 60 to 120, we are expecting the variability or the standard deviation to decrease. So you'll notice right here in a very small print are the standard deviations. And the smallest standard deviation is the 0.045. So I'm going to say right there, that's a sample size of 120. The next smallest one right here, 0.065, I'm going to say matches up with a sample size of 60. And the biggest standard deviation, or the highest variability, goes with the 20 simulation. So it's as simple as that. The smallest standard deviation corresponds to the biggest sample size. Now the other thing you could make a note of is the smallest in the biggest value here. So this one I think has the tightest interval, okay, the shortest interval from smallest to biggest. And so again, that's another way of saying we've got the smallest standard deviation or the smallest variability right here. And you notice this one has a low of about 0.45 and a high way up at 0.95. And there's the biggest gap, statistically speaking, between the lowest and the highest. So I'd say this bear right here has the highest variability. Now I've got a little story here for you, and the context of this story will carry us through the rest of the video. And we've got about what feels like a million questions associated with this. But it says a high school principal claims that 50% of the school students walk to school in the morning. Now a student, and hypothetically we'll say it's you, you set out to attempt to verify the principal's claim by taking a random sample of 40 students, keyword there being random again, and asking them if they walk to school in the morning. 16 out of the sampled students said they usually walk to school in the morning, giving you a sample proportion of 16 out of 40. So you randomly selected 40 students, 16 out of that group said they walk usually, and giving you a percentage or a proportion of 40%, which seems to dispel the principal's claim of 50%. Shouldn't these numbers match up? Well, But could the principal be correct that the proportion of all students who walk to school is actually 50%? So let's start with a conjecture. Do we think we definitively disproved the principal's claim? Well, not exactly. Certainly, it is possible for one sample to have a proportion, to have a proportion of 40% or 0.4. Because our sample size was rather small. We only randomly selected 40. I say only. That's not a bad sample size by any means. But certainly, we could start all over and we could pick a totally different random sample of 40. And I think, it's possible to end up with a proportion of 0.6. And certainly the randomness plays a role, and maybe hypothetically you picked a third group of 40 students, and by golly, only 5 of them walked to school, and you'd end up with a really low percentage, and that'd be very rare, but it's possible, and that's what we're saying here. Certainly it's possible. Now we want to develop a plan and how you'd plan to respond, and maybe we could dig a little bit deeper into this. And ultimately, we want to try to answer this question right here. How likely is it to have a sample proportion of 0.4, assuming the principal was correct? And we don't have the time, energy, or resources to go out and repeat this survey, over and over and over again. I mean, theoretically, we'd like to do exactly what you just did here once and repeat it another 50 times and just keep grabbing another random sample of 40 and another one and another one and another one. But again, we don't have the resources. So what we're going to do is, believe it or not, we're going to flip a coin. Why flip a coin? Well, of course, when you flip a coin, you've got a 50-50 chance of getting heads or tails. And that 50% matches up with the principal's claim. Okay, and what we're going to do is we're going to try to create a sampling distribution of sample proportions just to answer this question: how likely is it for us to get a sample proportion of 0.4? And eventually, we're either at the end of the video, we're hopefully either going to support the principal's claim, or maybe we'll disagree with it statistically. The cool part tonight is we're going to use technology, whereas yesterday we really simulated. I think in the video we were talking about pulling M&Ms out of a container, and in class we were pulling beans out of the container, and it's a great activity to introduce you to it, but it does take some time, and tonight we're going to take advantage and use our technology to do our simulations. And the website that I'm using for everything tonight is rossmanchance.com/applets/coin tossing/cointoss.html. Great website to try to feel free to go play with it. I think you might get hooked, and that's my warning. If you go there, you might be there for a little while, because surely there's a lot of toys to play with there. But we are going to assume that the principal was correct here, that 50% of the population of students do walk to school, and we're going to designate heads to represent that a student walks to school, and by virtue then tails would be a student who doesn't walk to school. And what we're going to do is we're going to flip a coin 40 times, and we're going to write down our results here. So I'm going to go grab a picture of my simulation and bring it back in. And bingo, here it is. So here's what's happened. I set the probability to 0.5, which again represents 50% chance of heads. I said I'm going to toss it 40 times, and I'm just going to repeat that simulation once. And this represents all of the individual flips 40 times. I got 14 heads, and then by virtue I was left with 26 tails. Now, not exactly what I expected. I just thought automatically that if I flipped it 40 times, I'd get 20 heads and 20 tails, but that's not that's certainly not a guarantee, and here's kind of a freak one. So now the question is, based off of these results, what's my sample proportion of heads out of your sample of 40? And what we did is we got 14 heads out of 40 flips of the coin, which actually equals 0.35. Of course, 35% chance of getting a heads in my sample. And certainly, if I could flip a coin 40 times and only get 14 heads when I'm expecting 20, then certainly if you're going to go survey 40 students and ask them whether they walk to school or not, it's plausible that only 16 said they walked, when indeed you'd expect 20. Now what we're going to do is we're going to repeat exercises 1 and 2 and get another simulation. And so again, I'm going to go back to the website, and I'm going to grab a picture and bring it back and show you. And bingo! Here we go. So I flipped it a new 40 times. We reset, we started over. Here's my 40 flips, and this time I got 18 heads and 22 tails. So I'm a little bit closer to what I expected, but still not exactly 20-20. So my proportion this time would have been 18 out of 40 for a proportion of 0.45 or 45%, so closer than we were. Now, just for fun, just because I couldn't help myself, I want to do one more simulation and see if I can get anything, because of course I could err on the other side of where maybe I get more than 20 heads, and so let's run one more and see if that happens. And yes, indeed, this time we flipped it, and let's see, we got 21 heads this time, so our proportion on the third simulation, 21 out of 40, gave us a 0.525, and certainly you'd expect to err on the side of less than 20 just as many times as you expect to err on the side of greater than 20. So far I showed you 3 simulations of flipping the coin 40 times, and what if we had, let's pretend that we had a class full of 25 students, and each student did 2 simulations of flipping a coin 40 times. So we'd end up with a grand total of 50 simulations. I'm going to go again, use that technology, and I'm going to import what it would look like if we had a classroom of, where we did 50 simulations. And bingo, here is what our sampling distribution of sample proportions would look like. Remember, each of these dots represents one simulation of flipping a coin 40 times. And there's a grand total of 50 dots on this distribution. And in fact, if you refer back to the first 3 we did, we had one that was 0.35, which is that dot right there. Our second simulation was 0.45, so that's just the first dot of this entire column. And then our third simulation, we actually got over 50%. It was like 0.525, which would be the first one within this column. And again, just like yesterday, I described the shape of the distribution, and I thought, you know what? By golly, this one's roughly symmetric, approximately symmetric, and it's mound-shaped. What was the smallest proportion that we observed? Well, right here we had 2 different simulations that had a proportion of 0.30. And you know what's coming next. Which one was the biggest or largest proportion? We had one proportion out there at 0.68. Okay, so that's very rare to get one proportion of 0.68. And how about the center? Where is the center of the distribution? Notice they didn't say most often necessarily like yesterday. We're just looking for the center. And this is slightly debatable, but when we're looking for the center, the 0.45 was the most often, but I don't think that's necessarily the center. I'm going to say the center is right here where you'd kind of expect it to be, which is about 0.5, where we've got, probably 50% of the dots to the left of 0.5 and another 50% to the right. So I'm going to say, roughly speaking, 0.5 looks like the center of the distribution. And again, we could split hairs. If you wanted to argue 0.52 or 0.48, I certainly wouldn't put up much of an argument. All right, let's see where we're going next. Now, that other great thing about the simulation we did in that website that we're using, the Rossman Chance website there, is that it automatically reported, and you might have even noticed it when we first flashed that distribution on the screen, and that it showed us what the mean and standard deviation were. So I'm going to go ahead and I'm going to report those to you right now. Our mean was 0.498. Hopefully you weren't surprised by that. And the standard deviation was 0.079, which measures the spread of the data. So, and they want to know, how does the mean of our sampling distribution, which is this rascal right here, compare with the population proportion of 0.5, which is what we're expecting. Again, we're assuming that the principle was correct, and we're assuming that the population proportion is 0.5, and we're going to say they are very, very close, which is great. Okay, now let's get back and tie it in again with our principal's suggestion that 50% of the students walk to school, because that's really the one new thing that's new today. And here's our question. We sampled 40 students and found that our sample proportion of students was 0.4. About 40% in our poll walked to school and 60% didn't walk to school. Would this have been a surprising result if the actual population was indeed 50% as their principal claims? Well, let's go take a look and see how we're going to answer that question. We're going to scroll back up here. Now here, it's all about finding where is 0.4 here. On this chart, 0.4 is going to be somewhere in this neighborhood right here. So I'm going to assume that this row right here, this column I should say, lines up with my 0.4. I gotta shrink my pen size down just a smidge here. And I'm going to grab my red color. So I'm going to say right there's 0.4, 40%. Now what you'll notice is, let's count up all the dots within this neighborhood right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, there's 12 different proportions that were either at or below 40%, okay? Or I could just say 0.4 for my proportion. So, you know what? Our sample, although it wasn't the most likely one, it's certainly possible, as this sampling distribution has proven. And to ultimately answer their question, we're going to say that a proportion of 0.4 was not surprising, okay, because our distribution shows that it's certainly possible. Now you ask yourself, well, what do you mean that's not surprising? I guess what would be surprising? Now, if I had gotten, let's say I had gotten a proportion of, say, 0.2, way down there. I said, now that's surprising, because what we're showing here in this distribution is that we did a lot of simulations, and not once did we get a 20%er, or on the flip side, maybe you got 80% of the students you surveyed said they walked to school, and I just said, by golly, 80%. That's really surprising, because again, not one sample in our large pool of simulations was at 80%. Okay, again, I just imported the same sampling distribution that we had on the last screen, just a little bigger this time. And the question is, what do you think would happen to the sampling distribution that we just constructed had everyone in your class taken a random sample size of 80 instead of 40? So this time, we're going to just randomly choose 80 students in the school instead of 40. And what do you think would happen here? Well, what I expect is my mean to stay roughly the same. If anything, this is going to get even closer to 0.5, even though 0.498 is so close to begin with. And then what I would expect is, as that sample size increases, I'm going to expect my standard deviation to decrease, okay? And what we're going to see is that all these points are going to cluster even more closely together than they already are. I'm going to expect my lowest points to get closer to 0.5. I'm going to expect my highest points to get closer to 0.5. And everything's just going to tighten up and bunch up in the middle closer to 0.5. So let's go ahead and write that down. We'll say the mean was going to stay approximately the same. If anything, it would get even closer to 0.5 than it already is. And we're going to comment here that our standard deviation is going to decrease and get much smaller. Well, naturally, the question is, why don't we do what we just suggested? Why don't we simulate 80 coin flips instead of just 40? Because we're thinking the bigger this number is, the better, more accurate results we're going to get. So here we did. I went back, I reran my simulation, I changed my number of tosses to 80, and I said, let's just do one simulation for now. Here's 80 different flips. We got 42 heads. We got 38 tails. What is my proportion of heads? Well, let's see, 42 divided by the 80 flips, that gave me a 0.525, or 52.5%. Now, let's say again, just like we did before, let's say there's 25 students in your class and they each perform 2 different simulations of 80 coin flips. Now, here's what the sampling distribution of the sample proportions might look like. I'm going to go grab a picture and bring it back with me. And I took a much bigger picture this time to show you some of the other details on that website. You'll notice the big thing that changed was the number of repetitions right here from 1 to 50. In other words, repetitions is simulations where it redoes the 80 flips. And this just shows the last repetition out of those 50. The last one was literally 40-40 or 50, 40 heads, 40 tails for a 50-50. And then here is the sampling distribution that I usually enlarge. So that's probably what I'm going to do on the next slide is I'll cut this part out right here and blow it up a little bit so we can read it. But you'll notice my minimum value is bigger than it was last time, and my maximum value is smaller than it was last time. And we're more tightly bunched, a little closer to 0.5. Compare this standard deviation to the one we had earlier. So here is that cutout. I tried to blow it up, but it got a little blurry on me here, but I think we could still read it. Let's do this. Let's describe the shape. I'll tell you what, very, very similar here. It's not quite as tall in the middle as I'd expect, but we do kind of see the symmetric behavior roughly, but very roughly. I was actually quite surprised in this one. The smallest proportion, what do we got for the smallest one? It looks like it's right around 0.4. Hard to tell exactly where the dots line up, but we'll say approximately 0.4 was the smallest proportion. And then the largest one is this real random one out here, is that 0.64? 0.63 maybe for the largest one. But I tell you, that's a real random one. If that bear wasn't there, then we'd say, probably 0.59 was the largest one. So kind of an outlier, as we like to say, for that 0.63 almost. Now, using our technology, we can find the mean and the standard deviation, and that's sitting right up here on the screen, so we could write those down. And the big key here is look at your standard deviation. Compare that to the last time. The first time we did this simulation, when we were only doing 40 flips, it was 0.079. That's what we wrote down earlier. And then this time, and I'll use a subscript of 2, is 0.061. So that's what we consider a big drop. I know the numbers are pretty small, but that's what we consider a big drop in the world of statistics. All right, here we go, coming down the home stretch. Number 18 here. How does the mean of the sampling distribution based on 40 flips compare to the mean of the sampling distribution of 80 flips? So we've got our two sampling distributions of sample proportions. I'm going to compare this mean to that mean, and by golly, are they very, very close. And that's what we want to stress. The means are very close, very similar. And that's what we'd expect. If we went from 40 flips to 80 flips and then we upped it to 200 flips and then 500 flips and 1,000 flips, we'd expect that mean to stay really, really close to 0.5. It's not going to change very much. Now, how about this, though? This is going to change things. Describe what happened to the sampling variability, or describe what happened to the standard deviation when the number of flips went from 40 to 80. And your distribution, your deviation went from 0.079 and it dropped to 0.61. So we're going to say the standard deviation, our lowercase sigma, decreased. And that's what we expect it to do every time the sample size increases, and that's a theme that's really been reoccurring throughout the last two videos. Okay, now what do you think would happen to the variability if we increase the sample size to 200 instead of 80? And I'd say we would expect that sample standard deviation to decrease even more. Maybe it was just 0.061. Maybe it would drop down to 0.4 something, into that ballpark. And now recall, let's go back and see if we could tie this together with the question we started the video with. Now remember, we took a random sample of 40 students, and we found out that a sample proportion of students who walk to school was 40%. I think it was 16 out of the 40 responded that they do walk to school. Now, if the student had taken a random sample of 80 students instead of 40, would this have been a surprising result? And let's go back and look at that chart. Remember, when we only did 40 flips, we said 40's right here. And he said, you know what? You've got 4 students here, 2 more, 3 more, 1 more, 2 more. There was a pile of students that were 40%, or a pile of samples that had a proportion of 40% or less. They said, based on that, it's not that surprising. But when you compare it over here and you see where the 0.4 is, and you see how it's closer to the left edge, and now it gets harder to buy the fact that 40% of the students walked if the true percentage was 50. So we're saying, you know what? By golly, it actually is pretty surprising. And here's exactly how I would word my response, and I would try to hit on as many of these ideas as I could. So generally, this would be a very surprising result. The value of 0.40 is now about 2 standard deviations from the mean, and only 2 of the simulated samples were actually less than 0.4, which makes a sample proportion of 0.4 a very surprising result. It just seems to be very rare compared to where the other clusters are centered.